Okay. So, this is the class in which we will start our discussion on some other structures. In the last class we studied about remaining structures based on FCC packing of anions and some other structures like perovskite structures, cesium chloride structures, and so on. In this class we will take on some of the structures which are technologically important of technologically important materials, and they are based on, for instance, the perovskite packing of structures. So, in this they are not exactly perovskites, but what happens is the structure looks like as if perovskite units are stacked on top of each other, and this happens typically along C axis, or there is an twinning of perovskite structure with some other structure such as sodium chloride. So, mostly these structures are showed by materials like superconductors such as YBCO or ferroelectrics like bismuth titanate. We will look at only some of the examples, and rest of them, if you want to study them, you can go through them in the books. So, for instance, in YBCO, the parent compound is yttrium copper oxide, where copper is in +3 state, and this contains the stacking of YCuO3 perovskite units along the C axis. So, as you can see, if you multiply YCuO3 by 3, it becomes 3 perovskite units. So, now it is made superconducting by substitution of 2 of the yttrium ions by barium, which modifies the structure a little bit, followed by reduction of Cu3 plus to Cu2 plus, which creates some oxygen vacancies as well as reduction in the number of required oxygen atoms, or basically Cu3 plus Cu2O reduction requires less number of oxygen atoms in the structure. So, parent structure remains same, but some of the oxygen atoms from the previously occupied sites become vacant sites, and this kind of doping gives rise to a superconducting state in which material has 0 resistance, and the temperature below which this happens is 92 Kelvin or so. So, the final formula of the compound becomes YBA2 Cu2 2 plus Cu3 plus. So, 1 copper remains in Cu3 plus state, 2 coppers become in 2 plus state, and so stoichiometric formula should be YBA2 Cu3O7, but superconducting state requires some more deficiency of oxygen. As a result, it is YBA2 Cu3O7 minus X, where X is a very small number like 0.15. So, how it happens is you have Y3 Cu3O9, dope it with barium, so substitute for 2 yttrium. So, naturally, if you substitute for 2 yttrium, you have requirement of your requirement of oxygen goes down by 1. So, it becomes YBA2 Cu3O8. Now, Cu3 atoms reduce from +3 state to +2 state, 2 of them. So, the formula now becomes YBA2 Cu2 2 plus Cu1 3 plus O7 minus X, or if you do not count X, you could take it as 7. So, this is how the structure is going to look like. So, this is the 3 perovskite unit stacking along 001. You replace 2 yttrium ions in the top and the bottom unit cell by barium. As a result, some oxygen is not required. So, to account for requirement of less oxygen, you have these vacant sites of oxygen which was previously occupied, and now further when Cu3 plus, some of the Cu3 plus reduced to Cu2 plus, then also the requirement of oxygen goes down, and you have some more oxygen vacancies created at these positions, for instance. So, so this is how the structure looks like, and the correct form, the structure, this is the whole unit cell of YBCO, and if you look at the coordination of copper atoms, there is the interesting thing about this structure, that copper has 5-fold coordination in these locations. So, you can see 1, 2, 3, 4 and 1 here, and along in these positions copper has 4-fold coordination. So, copper tends to have 3-fold and 4-fold coordinations in various positions. So, Cu3 plus typically has 5-fold coordination, Cu2 plus will typically have your 4-fold coordination. So, another structure which is interesting is lanthanum strontium copper oxide, which is for which the parent compound is lanthanum copper oxide. So, in this lanthanum copper oxide, which is actually a mixture of rock salt structure compound LaO and one perovskite structured compound LaCuO3, and you can, for convenience, you can write it as LaO.LaCuO3. So what happens here is, when you dope this material with strontium, replacing some of the lanthanum ions, this again becomes a superconductor, and it gives a transition temperature of about 35 Kelvin. And the structure shows basically a layered structure in which you have A4O layers, which means one oxygen is surrounded by 4 A's, followed by AO4 and then CuO2, etc. So this is how the stacking continues, as I will show you in the next slide. So if we go to the next slide, if you look on the left, you have these two perovskite layers which together make NaCl structure layer. Now if you look at top NaCl layer, perovskite layer, top perovskite layer is shifted with respect to the bottom perovskite layer by the vector half 110. So basically the origin of the bottom layer is here, and I have shifted the origin of the top layer to the on top of face center, on the top of trough face center of the bottom unit cell. So this has gone from this position to that position, which is actually along 110 direction in the xy plane. And if you look at the structure, it looks like, so you have CuO2 layers, which are these CuO2 layers, followed by AO4 layer, where each A atom, which could be lanthanum or strontium, surrounded by 4 oxygen, followed by A4O layers, then again followed by CuO2 layers. And if you look at the CuO2 layer, the configuration has changed from here to here a little bit. So that you have to remember, and as a result the structure continues itself. So CuO2 AO4 A4O, CuO2 A4O AO4, and so on and so forth. It just keeps going down in the same fashion. So this would be your lanthanum strontium copper oxide structure, which is superconductor. So it looks a bit complex, but if you look at the structure in a different way, thinking that it's a mixture of NaCl and perovskite structures, the understanding becomes more clear. And this is how most of the complicated structures are made of, especially in superconductors and in ferroelectrics. Now we will look at the structures which are based on HCP packing of anions. So here anions, typically oxygen, they make a HCP lattice, and cations occupy either tetrahedral or octahedral sites depending upon the radius ratios. So the first the structures in this series are Wurtzite, Corundum. Wurtzite is your typical zinc oxide kind of structure. It is a polymorph of previously studied sphalerite or zinc sulfide or zinc blend structure. You have Corundum, which is the parent structure of alumina, alpha alumina. Then you can have ilmenite, lithium niobate, and rutile. So we will go through these one by one in this lecture. So Wurtzite, we will start with Wurtzite. Wurtzite structured compounds have a stoichiometry of 1:1 for cation and anion, and they are referred by general formula Mx. And the examples, as I just now mentioned, these are polymorphs of sphalerite or zinc blend structured compounds, which are zinc sulfide or zinc oxide or silicon carbide, etc. Here in this structure, what happens is the anions, which could be sulfur or oxygen atoms, they form a HCP lattice, right. Now since they are polymorph of zinc blend structure, if you remember in zinc blend structure we had FCC packing of anions with half of the tetrahedral sites occupied. Now same happens here, it's just the structure is different. So packing sequence of anions changes from ABC ABC to AB AB, but still the covalent bonding contribution requires the material to have tetrahedral coordination as well as radius ratio in these compounds. And so half of the tetrahedral sites will be now occupied by cations. So whereas anions form in the sequence, it should not be ABC ABC, it should be AB AB AB. ABC 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 would be true for zinc sulfide or sphalerite structure. And the coordination of both anions and cations, just like in zinc blend structure, would remain 4. So there is no change in terms of packing and interstitial side occupancy with respect to zinc sulfide, which is a zinc blende structure or sphalerite structure. The only change is that the anions packing is now AB, AB, AB instead of ABC, ABC, ABC. So, the structure is something like this. So, you have, this is the layer of oxygen atoms, this is the layer of zinc atoms, again you have a layer of oxygen atoms, again you have a layer of zinc atoms, followed by oxygen atoms. So, this would be your A layer, this would be your B layer for anions, and then again this would be of A layer. And if I zoom this particular part, which is the drawn unit cell, then it looks something like this. So, you have these top oxygen atoms, bottom oxygen atoms, and the central oxygen atoms. This makes one hexagonal unit cell, and these are the tetrahedral sites which are occupied. So, these are and if you count the number of atoms, total it would be 2 per unit cell for both types. So, you can see here that in this, if you draw the plan view perpendicular to parallel to C plane or perpendicular to C axis, you can note the positions of both cations and anions in this fashion. So, cations, so your anions will be at 0, 0, 0, and if I consider this as x and this as y, then my anion would be, it would be 2 by 3, 1 by 3, 0, depending on how you look at it, it could be 1 by 3, 2 by 3, 0, or 2 by 3, 1 by 3, 0, and cations will be at the edges. So, this would be at 0, 0, 5 by 8 and 2 by 3, 1 by 3, 1 by 8. So, now if you look at the structure, only half of the tetrahedral sites are filled, and if you remember from HCP packing, in HCP packing you have tetrahedras which are pointing downwards, tetrahedras which are pointing upwards. So, in this structure what happens is the structure is such that all the tetrahedras are pointing upwards, or all the tetrahedras which are pointing in one particular direction are filled by cations. This is the polyhedral model. Of course, you can invert it, you can put it upside down, and you can show that it is all, but the point is they are all pointing in one direction. You can say up or down depending upon your frame of reference. So, the way it is made, the structure, you make first layer of oxygen atoms. So, this is the closest packed layer, C plane. Now, the interstitial sites are either these or these, any of these could be filled. So, let us see. The second layer, the first interstitial layer goes in these sides. I have chosen to put it there, you can put it here. Now, the second layer of oxygen atoms goes on top of these, which I have chosen to fill. This I have left it empty. Now, in this case it would make octahedral site. Okay. So, octahedral is not filled, we leave it empty. We have filled only tetrahedral site. Now, what will be the other tetrahedral site? Other tetrahedral site is this. So, this would be tetrahedral of one type, this is the tetrahedral of second type, this would be octahedral, which is empty. So, these sites are labeled as T2 will remain empty. So, when I put the next layer of zinc atoms, where are they going to go? They are going to go into positions where tetrahedras are pointing in one particular direction. So, we will see. So, now I put the second layer of zinc and oxygen atoms, and they go in the positions which are again pointing upwards. So, these are the ones which will be pointing upwards. On the other hand, if you look at the position. So, in the first layer one particular type will not be filled, in the second layer another particular type will not be filled, which will be both pointing upwards or pointing down. So, this would be your formation of zinc oxide structure, and this would be one unit cell. This brown one would be one unit cell of zinc oxide containing 2 atoms. So, this is how Wurtzite structure is formed. Second structure in this series is Corundum structure. Corundum is based on parent compound Al2O3 or alpha alumina, and this is the Corundum is a mineral name. Stoichiometry of this compound as a result is M2O3. So, 2 anions are there for 2 cations and 3 anions from this formula unit. Parent compound, as I said, is alpha alumina or sapphire. The other compounds which follow this structure are, for example, alpha iron oxide or chromium oxide. And as per the radius ratio, in this structure, the cations, the anions form FCC packed structure, which is AB-AB kind of packing, but the cations in this structure based on the radius ratio occupy octahedral sites, not the tetrahedral sites. As a result, the cation coordination will be 6. Now, you can work out yourself from the bond valence rule, or bond strength rule, as we saw in the previous cases. To fulfill the stoichiometric requirement, the anion coordination has to be 4. So, now as a result, since you have now AB packing, on for 3 anions you have 2 cations, which means only 2/3 octahedral voids will be filled, because in a closed packed structure there is 1 octahedral site per atom. So, you have 3 atoms of oxygen, which means only 2 of octahedral voids will be filled. So, you have 2/3 filling of octahedral voids. So, the structure is formed in the following manner. In this animation, I put the first layer, which is oxygen, and I put the second layer, which is the aluminum first layer, and the aluminum arranges itself in this kind of fashion. So, since you have 1/3 sites, octahedral sites empty, these crosses show the empty sites and other atoms show the filled sites. Now, second layer, when the second layer is formed, this vacant site will move from this position to that position in the next layer. So, let us see. So, this is the second layer of oxygen atom. So, naturally this is the octahedral site between the first and second layer of oxygen. In between you have aluminum atom, and if you put the second aluminum layer, so you had the cross in this position, now the cross has gone there. So, this is the vacant site which is moved along a particular axis in the next layer, and when you put in the third layer, it will come back again here. So, it goes in this fashion and then comes back here. So, when you put the next layer, this is the next layer of oxygen atom, and the next layer of aluminum atom goes there. If you keep doing this and you stack 6 layers of oxygen on top of each other, then you form the whole unit cell of alpha alumina or corundum. And you can look at the cross section of this structure, which explains the structure in slightly better way. So, let us say if I look at 10 plane, which is this plane, then this is how it looks. So, you have this first layer of a layer of, let us say, oxygen, followed by octahedral site filling. So, you have 2 filled and 1 empty site, followed by second layer of oxygen atom, followed by again 2/3 filling of octahedral site. But if you notice that the position of octahedral site has changed, and then you fill the third layer of oxygen, a layer, then again the cation layer, then again you see that the site changes in a sequential manner. So, first this one was empty, second this one was empty, and now this one is empty. You could have made this one empty, that one empty, and that one empty. So, it does not really matter. So, if you just keep doing it 6 times, so you have a first layer, second layer, third layer, fourth layer, fifth layer, sixth layer. This makes the whole unit cell, and this would be your C parameter of alpha alumina. And you can label the directions. This would be C axis, so 0 0 0 1 direction, and this direction would be 1 bar 2 bar 1 0. You have to make sure that the dot product of since this is 1 0 bar 1 0 plane, the dot product of this plane with these 2 directions has to be equal to 0. So, this is how you stack 2 different kind of atoms while you form this corundum structure. And as you can see, these are the columns of filled octahedras, alternatingly filled. So, these arrows point out these columns of octahedra, which share each other's faces. Now, the second structure which is important in this series is ilmenite structure. Now, ilmenite structure has same formula as a perovskite structure, that is AbO3, but it is not a peroxide structured compound, rather it is based on the corundum structure. So, it is a hexagonal close packed structure in a similar fashion as Al2O3, except that the difference is in the Al2O3 you have for 3 oxygen 2 aluminum atoms, here for 3 oxygen atoms you have 1 A atom and 1 B atom. Now, the common example for this common compound or parent compound for this structure is FeTiO3, iron titanate. Other examples are, for example, cadmium titanate, cobalt titanate and many other materials which follow this structure. However, iron titanate is the most commonly known compound for this structure. So, atomic arrangement is similar to Al2O3, except that in one layer you have iron, in the second layer you have titanium, and the site filling sequence is similar to as you have in aluminum oxide. So, coordination numbers, both iron and titanium, since the filling is according to aluminum oxide structure, site filling remains same. So, iron and titanium both remain octahedrally coordinated. However, the coordination of oxygen now changes, it is coordinated by 2 titanium and 2 iron atoms, but it is coordinated by 4 cations. So, the structure, the way it forms is, you have first layer of oxygen followed by first layer of iron atoms in the octahedral sites, followed by then this arrow again shows how the vacant site will move in the next layer, and then this is the second layer of oxygen atom. So, this is A layer, this is B layer, followed by now next layer will be titanium. So, this would be your titanium layer. Okay. But if you notice, the vacant site position is same as in aluminum oxide structure. Then you will have next layer of oxygen atom, which would be again A layer, followed by next layer of iron atom, which would go right on top of the first layer of iron atoms. Then you will have this structure formed if you keep doing it 6 times, and so the whole structure will consist of 6 layers of cations or oxygens, and this will make a complete ilmenite structure. Again we can look at 10/10 plane, first layer of oxygen, followed by first layer of iron, followed by B layer of oxygen, followed by first layer of titanium. If you notice, the vacant sites remain same, except that now aluminum atoms are replaced in one layer by iron, second layer by titanium. Then again A layer of oxygen, then again second layer of iron, followed by second layer of titanium, followed by again oxygen, again iron, again titanium, then oxygen. So, this will whole make one unit cell of iron titanate. Again you can mention the directions just like that. So, this is how, and again these are the phase sharing octahedra, but now regularly alternatingly occupied by iron titanium vacant, iron titanium vacant. So, this is how it is going to be occupancy sequence. So, this is another important structure which is ilmenite structure. Now, in this series the next structure will be your lithium niobate structure. Now, lithium niobate is an important compound. It's ferroelectric in nature, it has optical properties which are of technological importance. We will discuss that in the next slide. So, if we go to the next slide, so again lithium niobate structure is very similar to aluminum oxide. By this I mean that the anion sublattice is same. So, anions pack in the same manner as they pack in aluminum oxide. Now, the difference is now in each layer where aluminum was, both lithium and niobium go, but they go in an ordered manner. So, that lithium and niobium occupy the aluminum positions in an ordered fashion, so that the structure becomes repeatable. So, it's different to FeTiO3 where Fe and Ti occupy the octahedral sites in alternating layers. Here both the atoms stay in the same layer, but in an ordered fashion. So, this material, as I said, is ferroelectric in nature, which makes it important from the point of view of technology. This also has a highly anisotropic refractive index, which is anisotropic means it is direction dependent. So, it is high in one particular direction, low in another direction, and it also shows birefringence and which can be changed by application of electric field. So, these properties make this material important from the point of view of applications, device applications, and it is used in electro-optic devices quite commonly. So, this is your lithium niobate 0001 plane. So, if you now look at this, so the yellow atoms represent the layer of A layer of, let us say, oxygen atoms, and now if you look at here, these red and green atoms, red is niobium, green is lithium, they occupy the octahedral sites and the crosses represent the empty octahedral sites. So, if you look at, if you suppose the color of both of these small atoms was same, it would make aluminum layer in aluminum oxide. Now, here if you notice, both of these are occupied in such a manner, so that in one position lithium is surrounded by 3 niobium, in another position niobium is surrounded by 3 lithium. So, this is how the structure looks like, or if you make it a hexagon in this layer, the apex of the hexagon and the vertices of the hexagon are alternatingly occupied by lithium and niobium atoms. So, this is how it is going to proceed when you stack this structure. I am not going to show you the stacking because it is very similar to in the previous two structures. I am just going to show you the cross section of 10 plane. So, here you have again AB layers, these are the oxygen layers. In between them you have, so lithium niobium cross, which is the vacant side, then again lithium niobium vacant side. Then in the next layer, since the vacant position moves in this direction in all the structures, so you will have again niobium vacant, lithium niobium, then again you will have vacant. So, this is how it continues, again 6 layers of oxygen atoms, and this makes a lithium niobate unit cell. Again columns are columns of octahedral sites, and you can again see lithium niobium vacant, lithium niobium lithium vacant, niobium lithium vacant sites. The difference to FATI structure here is, here if you notice, this lithium and niobium atoms, they make a charged dipole, which is a reason for this ferroelectric nature of these compounds, and all these dipoles are pointed in one direction, which do not cancel each other. And if you go back to iron titanate structure, there also you have dipole formation, but both the dipoles are oppositely oriented and they cancel each other, hence it is not a ferroelectric material. So, this is one of the peculiar observation in this material. So, this would be your dipole. So, these are the structures which are based on perfect HCP packing of anions. The last structure in this series is going to be your titanium oxide or rutile structure, which is based on HCP packing, but it is not exactly perfect HCP packing, rather it is called as a quasi HCP packing of anions. So, we will look at that structure in little detail, and following that we will summarize this module, and in the next class then we will start with a different module. So, the next slide is on rutile. Now, rutile is a very well known material, it is used as pigments etc. in applications, and it is basically a polymorph of a well known titanium dioxide. Other forms that can be available are anatase and brochite, but rutile is something which is very well known for variety of reasons. Now, in this structure you have quasi HCP packing of anions, which means anions pack in the same fashion as in a FCC structure, but there is some distortion in terms of spacing of atoms and formation of perfect hexagon. So, it is not exactly a hexagonal structure, but sort of quasi HCP structure. Now, again in this structure based on the radius ratio, you have octahedral side filling bications, which means which means titanium goes to octahedral side having 6-fold coordination. Now, if titanium is coordinated by 6 oxygens, based on the stoichiometry, oxygen will be coordinated by 3 titaniums. So, this is something, or it will have triangular coordination. So, this is something which you can again verify using bond valence or bond strength rule. And since you have for 2 anions 1 cation, only half of the octahedral sites will be filled. So, when we form the structure, the resulting structure does not have a hexagonal form, rather it is tetragonal in nature because of slight distortion of the structure. So, that is why this HCP packing is referred as quasi HCP packing. This material again, it has anisotropic diffusion properties, and cation, which is titanium, it tends to diffuse, it tends to have different diffusivities in different directions, and this makes this material very interesting. And also it has a very large and anisotropic refractive index, which is again technologically useful, and this also tends to have high birefringence, and this is commonly used as pigment and for some other optical applications and electronic applications, and is in general non-toxic applications. Hence, it is also useful for some biological applications as well. So, this is the structure, this is how the structure is formed. You have this one layer of oxygen atom, which forms itself in the same fashion as in a HCP structure. So, you can look at this hexagonal array of oxygen atoms, and if you look at the structure, the octahedral sites are now filled by titanium, but you see in this particular direction all the sites are filled, in this particular direction all the sites are empty, then again you have a column of filled sites, then again you have a column of empty sites. So, this tells you that 50% of octahedral sites are filled. Now, the unit cell has its corners, if you look at the unit cell from top, for example, unit cell has its corners on titanium atoms. So, it makes, this is the basal plane, for example, of a tetragonal structure, and this would be your A axis and this would be your C axis as denoted below. And if you look at now the whole structure, so when you put the next structure, next layer on top of both oxygen and atom, oxygen and titanium, you see something like this. So, you have a bottom layer of titanium atoms with oxygen atom. So, this is the whole layer of, so you have first layer of titanium, second layer of titanium, third layer of titanium. Between them you have oxygen either top, either below or under the layers. And if you look at, excuse me, and if you just connect these oxygen atoms, they form an octahedra, and center of this octahedra is occupied by titanium atom. And if you look at each oxygen atom carefully, each oxygen atom is occupied by, each oxygen atom is coordinated by 3 titanium atoms, because none of these oxygen atoms are perfectly within the plane, they are slightly out of or above the plane, and their positions are not exactly in the center of the planes. As a result, they tend to be closer to 3 cations than anions. And if you look at the polyhedra model, the polyhedra model looks something like this. So, octahedras at the corners. So, since all the titanium atoms will be coordinated by octahedras at the corners at pointing in this direction, and octahedra at the center will be pointing in this direction. So, it is a structure in which some half of the octahedras will be pointing in this way and half of the octahedras will be pointing in this way. So, this will make a this way and this way. So, this will make a titanium oxide rutile structure. So, in summary, we have gone through variety of topics. We started with the discussion on lattice and bonding. We went through the concept of point lattice, what a point lattice is, what is a primitive lattice, what is a non-primitive lattice. Those concepts are very important in order to understand the structures. And then we looked at what are the possible crystal systems and what are the possible Bravais lattices. We saw that there are 7 crystal systems and 14 Bravais lattices, which completely in which all the possible crystal structures can be differentiated. Since the choice of unit cell is not unique, as a result you have to define certain way of categorizing them. So, this forms a basis of 7 crystal systems, and then symmetry comes into picture, which takes us to Bravais lattices. So, you have, for example, simple cubic, body centered cubic, face centered cubic structures, and then various other forms of orthorhombic and tetragonal structures, and then rhombohedral, monoclinic, triclinic and hexagonal structures. So, these were the structures. Then we looked at some formation of planes and directions very briefly. Then we reviewed the bonding. In bonding, we looked at metallic bonding, covalent bonding and ionic bonding. In most of the ceramic structures tend to be ionically bonded with partial contributions from covalent bonding. since most of the ceramics are made from cations and anions, which in most cases have good difference of electronegativity, and this gives rise to very strong ionic bond. As a result, they also have high modulus and high melting points and low coefficient thermal expansion. And then we moved on to understanding the ceramic structures, and before that we also looked at how the atoms pack in metals, how the atoms pack in general, which actually form the basis of metallic structures, and voids between these spheres are interstices which form a very good basis for filling in ionic structures, because in ionic structures anions being bigger, they form the host lattice and cations occupy the interstitial sites. And then we looked at various possible structures, and we see that there are certain guidelines which govern the formation of these structures, which are called as Pauling's rules, and based on these rules you have certain coordination of each anion or each cation and anion, and the interstices based on the stoichiometry can be completely or partially occupied, and since the sizes of these atoms are often not perfect according to radius ratios, and also the shape of the atom may not be completely spherical, often you have deviations from the equilibrium structure. So there are structural distortions, but in most cases it's very easy to understand the structures. So most of the compounds follow three common structures. You have structures based on FCC packing of anions, such as rock salt, sphalerite and fluorite structure. So most of the ceramic structures, most of the ceramic compounds follow three common structures. There are structures where host lattice is made in FCC packing by anions. So ABC kind of packing of anions, examples of which are materials like magnesium oxide, zinc oxide, zirconium oxide, etc. And these are defined by parent structures. So you can have rock salt structure, which is a FCC based structure where cations occupy the octahedral sites, and based on the stoichiometry all the octahedral sites are filled. And you can also imagine this structure to have intertwined structure of two FCC lattices made by cation and anion. Similarly, you can have sphalerite structure. Sphalerite structures zinc sulfide or zinc blend structure, it is also often called as, and compounds which follow this structure are, for example, your zinc oxide, zinc sulfide, silicon carbide, etc. Here again anion make FCC lattice, however here the cation has tetrahedral coordination. Now based on the stoichiometry, it's there is only 50% occupancy of tetrahedral sites. As a result, you have a periodic occupancy of tetrahedral sites, which we looked at. And then we looked at fluorite structure, in which you can have fluorite or anti-fluorite structure. So for example, alkali oxides like sodium oxide, lithium oxide, they make anti-fluorite structure, where you have for each anion two cations, and both the cation and the cations have tetrahedral coordination. So oxygen makes FCC lattice and all the tetrahedral sites are filled by cations, and in this case the coordination of anion will be eightfold. So anion will have cubic coordination. However, lattice is represented by making a lattice unit cell on the anionic side, so it works pretty well. And this structure again has a FCC lattice. So whether you put the lattice corner, the unit cell corner on oxygen or any of the sodium atoms, it still makes FCC lattice. So you can also think of this structure as three FCC lattices interpenetrating into each other, two FCC lattices of cations and one of anion. And inverse of this structure is fluorite structure. There you have FCC lattice made by cations. This is the simplest way of understanding the structure, and all the tetrahedral sites of that unit cell filled by anions, like in zirconium oxide. However, the correct way of understanding this structure is making the base lattice of anions. Now since cations have eightfold coordination, which is cubic coordination, if you just draw in a cube, it is not going to fulfill the stoichiometry, because in one cube you will have only one cubic site. So what you do is that you make one big cube of 8 cubic unit cells of anions, and now you have in a big cube you have 8 cubic voids or body centers, out of these 8, 4 are filled by cations. So, this makes a fluoride structure or calcium fluoride kind of structures. Then we looked at the other structures like perovskite structure, cesium chloride structure. Perovskite structure is a very interesting structure from the point of view of applications. Many important materials like barium titanate, strontium titanate, etc., which they form perovskite structure. Typically, perovskite structure compounds are AbO3 compounds, where you have a cube. For instance, the perfect form has a cube. The face centers of this unit cell are occupied by oxygen, and body center is occupied by the smaller atom, which is typically B, and the corners of the unit cell are occupied by bigger atom, which is A. However, most of the materials in ferroelectric form show a non-cubic structure. It could be tetragonal, rhombohedral, orthorhombic, depending upon the temperature and type of material, but the pattern remains same. So, that is perovskite structure. You can also have perovskite structure where cation and anion can have +3 valence, and you can also have mixed perovskites such as PM and lead magnesium niobate or lead scandium tantalate. Then we looked at cesium chloride structure, which is whose parent structure itself is cesium chloride, where you have cubic coordination, and since stoichiometry is 1:1, it is just formed within a cube. So, corners of cube are occupied by one ion, and center of the cube is occupied by another ion. It is a primitive cubic structure. So, both perovskite and cesium chloride are primitive cubic structure. A variation of perovskite structure is rhenium oxide structure. So, in AbO3, if you remove A, then it is a BO3 kind of structure that makes a rhenium oxide structure, such as in tungsten oxide. And then we looked at some of the special structures which are based on perovskite packing of perovskite layer stacking, such as in yttrium barium copper oxide, which forms the basis of superconducting compounds. And then we looked at HCP packing of anions, examples of which were Wurtzite, Corundum, lithium niobate, and iron titanate, etc. So, here in these structures, the anions form the HCP packed layers, and either tetrahedral as in Wurtzite or octahedral as in Corundum, Ilmenite, or lithium niobate, or in titanium oxide as well. The octahedral sites are occupied by cations, and the occupancy is determined by the stoichiometry. So, this is a very what I can say is reasonably long discussion on the structures of ceramic materials. So, I hope you are able to understand the fundamentals. In the next class, we will move on to a different topic, which is important from the point of view of functional properties of these materials. So, in next class we will look at what are the defects in these materials, how the defects form, what are the how the defects are related to parameters like temperature and pressure of oxygen, and so on and so forth. So, I hope that you are now able to understand the structures of these ceramic materials in a good detail. Thank you.